Hello, my friends. Hello, my radio frequency and microwave design engineers, researchers, inventors. Good morning. I'm Dr. Mohamed Nezami, coming to you from Jerash, Jordan. Welcome back. We had a good summer and we're ready to start a new series. And this series, as I advertised on my LinkedIn page, will be covering the design aspects of slotted waveguide antenna arrays. And so basically, we will cover the theoretical background, and we will uh, basically also use illustrative examples. The intention is that we want to start out with a principle of a single slot in a waveguide, rectangular waveguide, either standard or custom, and then move on to building a larger aperture from slotted single waveguide, which should be fun. Okay. Now, for those of you that would like to contact me for any consulting design work, this is my email and this is my phone number. Now, as you may recall, I do consulting, freelance consulting. I design boards, basically PCB, radio frequency circuits from anywhere from DC to 35 gigahertz using standard off-the-shelf ICs, components, high frequency components, and design printed circuit components for microwave and RF. My rate is very reasonable, very cheap compared to the rates that are charged in the US and Europe. I operate offshore, so you can always reach me out at this number. I can give you a start up. I will work with you on the concept first. Um, that is if it's a new design, and then move on to specifications, and then do the actual theoretical work in system simulations using System View and HFSS and MATLAB, and then on to actual BCB implementation using Cadence BCB and schematics. So active or passive, be it filters or low noise amplifiers or antennas, you can reach out to me and you will be very happy with very, very easy, rapid time in development. And also the cost is really, really cheap. So, all right, let's move on to today's topic. And today, what I'm going to cover is basically slotted waveguide antennas. Now, we know that these antennas are very much used in niche areas where I will show basically primarily for radar, weather radars or avionics radars, and some satellite terminal applications, satellite terminal and satellite transponders as well. So just as an illustrative, to illustrate the concept, starting out, you can see here that slotted waveguide antennas are nothing but actually a linear array of slots that are carved either on the broad wall or the narrow wall of a waveguide, and then they radiate, and they're placed at a specific distance from each other, and namely a half wavelength, and that's why they tend to be narrow bandwidth. And then also the placement from the center of the broad wall is either uniformly distributed or distributed according to one of the distribution Taylor or Chebyshev or binomial distributions, which are intentionally done to bring down the side lobes. So I will cover both of those, uniformly displaced from the center and ones that are done based on Chebyshev distribution or binomial or Taylor. So you can see the principle of the antenna is pretty simple. So you start out with a waveguide, you put a bunch of slots and you feed it. Okay, when we're talking simple examples, it could be as simple as this example here. Although now constructively for large aperture, basically what you need to do is you stack a whole number of them. And they could be distributed like this, where they can add up and make a round pencil beam radiation pattern from the transmitter. And then they can be fed, instead of when a single component is done like this, we feed it from the side, and the other side is shorted basically, and the distance from the short here and the center of the last slot is a half wavelength, so that actually the signal, a quarter wavelength, sorry, so that you see the short is almost is open. It is open, transformed by the quarter wavelength. But you can also distribute them like this, so you can see that they're stacked, and then the feed is coming from here. There's another waveguide behind this stack of waveguides with inclined slots that are basically feeding the signals. So we've got the feed either from here or here, and then we've got behind the stack of waveguides another waveguide that is basically coupling in the RF signal at the center of every slotted rectangular waveguide, okay? And so we're going to go more into this. So we're going to start out showing how you design this here, as simple as this, with 16 slots and 8 slots, and then move on to something that is larger, okay? Now, schematically, this is how this system here is done, basically. So we've got a bunch of waveguides that are carved in metal, and then we've got a lid on top of them, which is basically the slots. And you can see the slots. And this comes down as a cover for this. And the feed is basically every one of these waveguides has a slotted hole inclined in the back, and this feeds in the back. And you end up with a slotted array pattern like this, okay? Now, theoretically, really the theory of slotted waveguide antenna design is very simple, okay? So all it is that you start out on the left-hand side here. So, or let's go move on to this section here. You start out here, this is where you input of the signal, and that is assuming that this point is like this or like this, where you're feeding in actually with a slot on the back, okay? But in any way, you want to make sure that because of the currents on the surface of the waveguide, your first slot has to be placed at a quarter wavelength, waveguide wavelength, that is, at the center of it is a quarter wavelength. And then you basically place every half wavelength another slot, and you alternate them from the center of the broad wall. And I'll show you in a minute why we alternate them, why they're not lined up in one case. And it has to do with the direction of the currents. As you know, if you look at a pattern of currents and E field on the rectangular waveguide, it repeats, and it has a 180 phase shift every half wavelength. So that's why we do this, really, so that the E field sums up in phase. And then, of course, at the end, we have a short. Okay, so every one of these sides is shorted here, and every one of these sides is shorted, okay? And this is a mirror image from the center of this feed waveguide. This is a mirror image of this, okay? So just to show you. And this is schematics showing basically how symbolically a single section of this is designed. So basically we have the feed, we have the input waveguide in here, we have a slot, feeding slot inclined, okay? And then we have the regular slots in the stacked waveguide on top, okay? And these follow the same rules that I just mentioned. Quarter wavelength from each shorted end, and then a half wavelength spacing between each other. Now the space, the offset from the center of the broad wall, these are based on a either uniformly placed or placed based on a one of the tapering techniques that are used, Taylor series or Taylor polynomial or Chebyshev polynomial. I'll show in a minute what you mean by that. And I'll show the equations and some MATLAB code that is used to come up with these dimensions. So again, like I said, the design principle is really simple. So once you figure out all these, crunch them into MATLAB with your desired aperture size and the beam width and the gain. And then you can just basically go and construct it in one of the 3D EM simulators, either CST or HFSS, and then start tweaking and verifying that everything does work. And then, of course, you move on to the solid model, which you can work with a mechanical engineer on detailing that and making drawings that will go to the CNC machines and do it. And they're very simple to fabricate because a lot of times you can buy off the shelf these waveguides as tubes, as aluminum tubes. So all you need to do is just basically carve out in the CNC machine and just cut out these slots according to the desired dimensions. So the applications, like I said, of slotted waveguides are basically, a lot of times it's either military or civilian radars, drone detection radars. So basically, a lot of times, most times it's in the KU, X-band, some KA applications. But what I've seen is mostly it's used for some high power applications because, as you know, these waveguides can handle much more power than just a printed array of antennas using microstrip technology. Now, the pros and cons of this antenna is that the only thing is that it has a small, narrow bandwidth, and the reason is because, as you know, the placement of the slots is a half wavelength. So therefore, your performance is narrowed to a single frequency, and then it deteriorates as you go above and below that center frequency because you're not anymore half wavelength, nor you are quarter wavelength from the ends that are shorted. Okay. Now, easy to fab, of course, that's a con. It handles more power. That's about it. Now, what are the types of slotted and waveguide antenna arrays? We have two types, okay? We have one where we call it a standing wave slotted waveguide, and another one which is based on a traveling wave slotted waveguide. And it has to do with the fact that your waveguides, you either do a short on the end, and the placement of these is a half wavelength from each other, uniformly spaced from each other at a half wavelength from the feed point, okay? And in that case, this would be a standing wave array antenna because the wave just basically reflections in here come back and it's in phase and everything is constructed, so it's pretty consistent. And then the traveling wave slotted waveguide arrays, these are, we call them non-resonance. And the reason they're non-resonance is because the distance between the centers of the slots don't have to be half wavelength. They can be some other one. And so therefore, now, in this case, always the beam is orthogonal to the axis of the waveguide. So it's always 90 degrees from the axis of the waveguide, where this one here is not necessarily. And usually these are fed from the side because you have to terminate them on the other end. So you feed on one end, and then the other end has to be matched, terminated, so you don't have any reflections back. Where this one here, of course, we don't have any termination, so you can feed it in here, and just basically the waves construct. So what are the differences? They're listed here, okay? Almost 99% of the cases, it's always a standing wave slotted waveguide with half wavelength spacings between the slots, okay? So fed from the bottom here, narrow bandwidth, where the other one is a little broader bandwidth, okay? And fed from either side, beam is pointed not broadside to the waveguide wall, okay? Where this one here, it's basically broadside. Okay, so let's just start with the very basic principle of designing a slotted antenna, a waveguide antenna. Well, here's a rectangular waveguide that shows a section of a waveguide. The first thing you need to recognize that we have two walls. We have what we call the broad wall, which is what we refer to it as A, dimension A, in the textbooks and publications. And we have the narrow wall, which is this wall. Okay, so you either do the slots here or here. And these are two different performances, okay? And so, and even two different polarizations you end up with, okay, whether you have the slots in here or in here. And I'll show you in a minute. Now, the slots in here can be longitudinal, okay? But in here, they can't be longitudinal because otherwise they will not radiate because they're in line vertically with the current. So you need to rotate them at an angle and you alternate the rotations so that you get consistent uniformly emitting signal sources. Now, in my applications in here, what I'm going to do is I'm going to focus on two standard waveguides, okay, the WR90 and the WR62. These are the industrial designation of these two waveguides. These are the dimensions of these in inches, and these are the frequency of operations, okay? Now, one of them, the WR90, is from 8 to 12 gig. Okay, so that's basically what we call X-band. And then the other one, WR62, is from 12 to 18. That's what we call Ku-band. Okay, so I'm going to construct some of my examples in here or here. I'm going to start today just to illustrate the principle using HFSS with one that is WR90, okay, which is basically literally 0.9 inches by 0.4 inches, okay? Now, let's show the principle of how slotted waveguide antenna operates. Starting out with how the current distribution on a rectangular waveguide is actually patterned. If you look at a waveguide and you view the current on this, you will see that the current basically repeats every half wavelength, okay? And then the current has a distribution where it actually alternates in phase every half wavelength as well, okay? So now the thing that you want to do is that and let's also look at this. So what we want to do, of course, considering this and considering that the phase shift associated with this is like this, okay? So literally, if you require a wavelength, that means it's 90 degree. If a half wavelength, it means it's 180 degrees, okay? And so on, and it repeats. You really, if you look at the E field also diagram and the magnetic field along the Z-axis of the direction of wave propagation, you can see that the E field is all sinusoidal. So it's always going to be the same dimension, assuming it's a lossless propagation. And then you can see that it toggles between 180 degrees. So within a full wavelength, you will see the E field actually a full pattern. So that you actually do this. So what you want to do is the slots to really radiate from this. You need to distribute the slots accordingly so that they disrupt the currents, okay? And if you look at the current direction on these, you will see in a minute. So this direction is going in, where on the next one, the direction is going out, okay? This one is going out, this one is going in, so there's 180 degrees between this and this, but there's 0 degrees between the direction of this and this. So that's why we place these slots, alternate them so that to take advantage of the phase shift as a result. And you end up with a linear array of dipoles, basically, that will radiate that are spaced at a half wavelength, waveguide half wavelength, okay? So that's the principle. It's pretty simple. So what you want to make sure of is that the slots are placed exactly symmetrical along the center of the broad wall, okay? And then you want to make sure that the length of the slot, of course, is a half wavelength, free space propagation half wavelength, because it's modeled as a dipole, okay? The spacing between them is exactly a quarter wavelength, like it is shown in here. Not free space, but the waveguide wavelength, okay? And then the width of these slots, we have an equation, a bunch of equations that we will use to determine the length of these. Now, right now, you can see that the spacing from the center of these slots here is equal, and that's what we call uniformly distribution illumination. Otherwise, what you and you always, when you do this, of course, this is like in signal processing, like a pulse. A pulse. If you take a pulse and FFT it, you're going to get basically a sine x over x with the side lobes at 13 dB below. Now, that may not be acceptable to some communication systems, such as accurate high-resolution radars. So what you want to do is then you want to taper down these side lobes, and we do that with windowing or taper. So that's why we resort to the designing the distance, the placement of these slots from the center line here. We vary that based on a window function, and the window function can be Chebyshev, Taylor, or binomial. And what you will end up with is you will end up with a symmetry, because the sine x over x, as you know, it's from the middle, from 0 degrees onward, is exact replica of the other one. So you end up with slots being distributed and tapered to the one side, and then the other side equally and similar. Now, let's look at this nice diagram that shows these slots in a waveguide. As you know, like I told you, if the slot doesn't disrupt the current flow, it will not radiate. So meaning, like this one here, B, it will not radiate because it's alongside the current, and the current can just go around it. Where this one here, it will not radiate on the sun. Now, this one will radiate, but the placement of this is not good. You want to place it here where there's current flow. So this will radiate, this will radiate, this will radiate, and this will radiate, okay? So if slot does not interrupt the surface currents in the waveguide, it will not radiate. That's it. Now, then there are some names associated with these type of slots, like this one here, which is the most commonly used one for the broad wall slotted waveguide antenna, is basically called inclined. So we've got the inclined slot in the broad wall, and then the B here is longitudinal slots, okay? Longitudinal because along the current, and this one is here is inclined, this one is inclined, and so forth. And the transversal is G here, this one here, because it's perpendicular to that. So, okay, so let's now, so we've got now, depending on where you put the slots, either in the broad wall or the side wall of a waveguide for TE10 mode, you end up with really either a longitudinal slots on the broad wall like this, that will produce an E field that is vertical polarization, okay? Where the other one here, as you can see here, it will actually produce an E field that is horizontal polarization, okay? And of course, the placement of these slots, as you can see, it alternates in phase, so that because the current here is going up, current here is going down, is 180, so you do this so that synchronously you combine the signals. And the same thing done in here as well. Okay, so like I said, of course, for rectangular waveguide with TE10 mode, always the radiation pattern is actually going to be a broadside to the wall, the broad wall, or orthogonal, okay? And this makes it pretty neat because you can view it and so on. Now, when you draw this on HFSS, make sure you put the center of the HFSS constructed model, the center is right at the center of the waveguide, so that you can see actually the pattern is actually centered correctly. Otherwise, you end up with a geometry here, and the radiation pattern will be offsetted to at the center wherever that happens. Now, this one here if you look at the applications, most likely these applications are done like this. Everything is done like this so that you have actually a vertical polarization, because radar, you want to have vertical polarization, okay? But in some cases, this one is also used often, especially in boat and ship radars, because in there, as you can see, the sea is like this, and horizon is the sea, and you've got objects above the sea level. And what you want to do then is to maximize your radar cross section is you want to have a horizontal polarization rather than vertical. So there is differences when you're trying to detect the some objects above sea level at a distance than when you're trying to detect a cloud, rain, or a drone, for instance, in the sky. Okay. And it's beyond the scope of this to discuss the reasons. You can refer to the publications, but you can see these radars on boats and ships, and basically that's all of these are basically waveguide slots in the narrow wall, okay, like this. Now, of course, we talked about the waveguides being, a tube. Now, of course, everything you do in a waveguide, you can actually implement it using a substrate integrated waveguide, and that's what is shown illustrated in here. You can actually construct a slotted waveguide antenna from a substrate integrated waveguide. It's exactly the same. It operates. And then you can also construct the aperture like this, where the input comes in here, and you've got slots. Here. You've got inclined slots in the back that will leak the RF, feed the RF to every center of these waveguides that are placed. And this is very simple to construct. And there are some publications on this if you like to refer further to this. Now, let's look at some interesting pictures I grabbed off the net. You can see that here is one where it's, a rectangular aperture with a bunch of waveguides in there. And you can see the back in here, you can see a standard waveguide feed, okay? So you feed basically, and you've got a 90-degree bend to distribute the signal to the center of every one of these, okay? So the network, the feed network behind it is also simple. Now, here's one where you can see it's in the nose of the aircraft in here. This is the slotted waveguide array, and almost literally every airplane that you see has a radar in the front to detect for collision avoidance and for weather radar as well, okay? Now, this is what's inside the radar of a boat or ship when it's done on the sides of the waveguide, as you can see here. Of course, this is a missile, and you can see that there is also a slotted waveguide antenna array in here, okay, with a whole bunch of RF and microwave components behind it. This is actually a drone detection radar. The thing about this, of course, as you know, these antennas are they scan, so most likely they are put on a motor rotation platform that rotates it basically. So like this one here is fixed in the elevation, it's fixed because he's trying to detect on the horizon if there's anything crosses the perimeter that they are monitoring. So they fix this, and but it will scan the azimuth back and forth, or 360 degrees it could go. And that's so this is actually a waveguide, but with a cover, radon cover for protection. Now, so how do you start designing an antenna like this? The first thing is got nothing to do with the lower level of the slots and their dimension, their placement. Is basically you want to construct the aperture first. You are giving, as a system engineer, you're required to cover a certain geographic area with radar, for instance, and you can figure out basically, depending on your the maximum range that you would want to cover, the radar cross-section that you're trying to view, and then you come up with equations on the overall aperture size, which will then give you information on how many, the size of how many of these antenna slots you need, okay? So we start out with the simple equations that relate the gain to the number of slots and the waveguide length, and the free space waveguide length. And so you can start out with this equation here, depending on the range you're trying to cover, you end up with a gain that is required from your transmitter or receiver. And so to get that gain, you need to vary this at the specified frequency to come up with the number of slots that you're trying to cover. Okay. Or another way is you're trying to come up how many of these slots you need to cover a specific beam width, PW, bandwidth or beam width in this case. This is in degrees at a certain specific distances between the which is a half. That's this parameter here. That's basically lambda g over 2 here. It's the spacing, okay? Or the other way around, you can see the bandwidth is equal to this here, which will give you n. Or you can use the aperture basically as a function of gain, and the antenna efficiency you can figure out there. All these equations, system equations, they can give you basically the other. Now, how do you design these slots at a specific frequency? Now, really, the father of slotted waveguide antennas is Mr. Elliott, Dr. Elliott, and he has these two papers. If you download them, they're available on the net, and they're really the reference for all the equations that I'm going to use today and the coming series. As you know, today is introduction and building theoretical background, and then I will move on until I construct a complete aperture from slotted waveguides. Okay, so Mr. Ilya references IEEE publications and the transaction on antennas and propagation. He's got two papers in 86 and 83, and these are the references basically. But the design algorithm for slotted waveguide is really simple. All you need to do is just lay this out so that the first slot is from the feed point. Now the feed point, whether it's a waveguide feed point for a single one, or it's the center of an inclined coupling waveguide from behind, feeding from behind, from the bottom. Now you need to make sure that that's the center of that slot is a quarter wavelength. The length of the slot is easy. That's a half wavelength, free space wavelength. So you're giving a frequency you can figure out. And then, of course, at the end, where it's shorted, you need also a quarter wavelength. Now, this doesn't have to be a quarter wavelength exactly, because a lot of times you cannot use quarter wavelength because the slot will be, the length of the slot will come outside. So really, it's a multiple of quarter wavelengths, odd number of quarter wavelengths. So you've got 3 quarter wavelengths, you've got 5 quarter wavelengths, 7 quarter wavelengths, whatever you need. What I'm going to show you, the example I'm going to show you today, I use 3/4 of a wavelength. And basically, because otherwise this distance in here, if it's only a single quarter wavelength, the slot would have to come outside. It doesn't work. Okay. So these are the algorithm for designing this. And the total length, if you use a quarter wavelength, single quarter wavelength, is exactly 5 waveguide wavelengths. Okay. So you can know ahead of time how long this waveguide will be. Okay. Now the first one in this design considerations is the length of the slot is a half free space wavelength. Okay, that's one thing. That's SL in here. The inter slot distance is half of the guided wavelength. Okay, lambda g over 2, and that's the distance from the center to the center. Okay, the distance from short circuit end to center of the last slot, that's this distance, is a quarter wavelength or 3/4 of a wavelength or other multiples, odd number multiples of that. The distance between center of the first slot and waveguide feed is the same thing. okay? Same thing, you treat this one here, the same thing as a short, as that's basically because you want to locate these so that they come out exactly at the area where the current is maximum distributed on the surface of the waveguide. The distance between the center of first slot and, okay, we covered this. Slot width is less than or equal to lambda g over 20. There are some other formulas that I will use also. Now, the thing that it is not mentioned in here is the placement, which is X off here. X off here is that's the hardest one to design. But we've got the equations because the equations has to involve the coupling factor between these, okay? And so you alternate, the distances would have to be, and that's why this one is really neat to implement on the HFSS solid model, because all it is you got from the center line offset either positive or negative number, and these numbers can be equal. That's these X offs for uniform distribution, which will give you a side lobe of only 13 dB down, or it will be basically vary according to a window function, a shaping window. Now, if you've got MATLAB, of course, tools, the toolbox, that's the RF toolbox, you get this function in here. They have an object already programmed via Elliott equations, so you can actually utilize it in here, and you give it all these numbers that comes up with the design parameters. I don't happen to have this, but I'm gonna actually write an actual MATLAB code that will do this, okay? Now, so let's start out at the design, okay? So basically, we start out saying that the rectangular waveguide with the slots distributed like this is really acts like it's a bunch of conductances that are shunt. And then at the end, there is a short. So this is a circuit representation of a slotted waveguide from the feed point to the short side on the back. And you've got the distances between these, which is basically in here, it's lambda g over 4. So this becomes open. And then you've got a half wavelength between every one of these G's. Now, these G's, you can design them equal, which will give you the side lobe level is only 13 dB down, or you could use tapering, which will give you less than, will give you down to 40 dB shaping. And I will show you in a minute. Of course, let me jump ahead to this slide here. So you can see that the radiation pattern really follows. You can taper down these side lobes depending on which the distribution number in here. These are the coefficients in the array factor, which are basically derived from the equivalent model of this conductance shunt loading in here, okay? Now, let's read some more on this. And I will give you the MATLAB code to do this. I will put it in the either in the comments or either in the video information if I could put it in. Now, of course, tapering distribution, the ones that excitations, we have these, okay? So what you end up with is you end up, these G's follow a pattern that's according to one of these polynomials, and it's symmetrical usually. So you end up like, say, for instance, if this is 16 slots, you end up with 8 slots that are the same as the other 8 slots. You end up with a center that is maximum power, and then they taper down to the left and right. Okay, so that's why the inclined feed on the back comes right in the middle of the waveguide. So you end up one side, a certain distribution of offsets, and then on the other side is exactly the same. So mirror of each other. So we're saying here the slots in here, offsetted from the center for TE10 mode, are modeled as parallel conductances either equal, which is uniformly, in that case, would be uniformly distributed excitation, or taper. By the way, the antenna excitation deal with windowing, it's covered. I have a whole series of videos. Please refer to it. Go to my channel, sign up. Please subscribe if you don't mind. you can go back to here, and I show exactly there how you derive using MATLAB these window functions for various distributions and how you implement them. Back at the time, this was done for microstrip arrays, okay? So taper distance is based on taper distribution, which will the side lobe, you can go down anywhere from 20 to 40 dBs, okay, using the, of course, there is a little trade-off in doing that, as you know, and one of those trade-offs is that the main beam broadens a little bit. It gets widened, so. Okay, using the non-uniform distribution such as Chebyshev, Taylor, or binomial, or some other functions. With uniform slot displacement, all slots are at the same distances from the center. So that makes your fabrication really easy. An equation that relates the conductances, these are the GNs, to the displacement, which is xn, that's the displacement here, xn, that's the offset from the center of these slots. From the waveguide center line is produced for both uniform and other distributions, okay? In both the uniform and non-uniform displacement cases, the slots should be placed around the center line. Of course, we do that. Now, okay, so like I said, the how to do the tapering for antenna array feed networks, you can refer to my videos in here. All right, so now, what is exactly happening? Why is the slot in here? Okay, we know that the distances of the slot from the shorted end and from the feed point, we know what that should be. But the distance from the center line, if you sweep, first of all, let's look at this diagram that I grabbed from one of the references, and I will show you this right now on HFSS as well. You can see that, first of all, if you sweep the length of this slot, if it is somewhere at resonance, and you sweep the length of this slot length as a function of and monitor the conductances or the input impedance in here or susceptance, well, you end up with this kind of deal where it will resonate at the exactly when it's half wavelength, okay? At exactly if the slot length is a half wavelength, what will happen is that the input impedance on this side, it will be exactly real. You can see, and it will be maximum. The maximum impedance in here, and then the imaginary part of that impedance of those conductances of these here, these components in here, these loads, susceptances, you will see that this one will cross zero. So that's perfect. That's nice, because what happens is that you start out with closed analytical solution to the slot length, but then you have to tweak it on HFSS. So what you do this is that you can do this by monitoring where is the point where the real, the imaginary part of this of these G's in here will be exactly zero, okay, and that will be your exactly resonance frequency. And the same thing for the offset. Now the offset basically determines the ratio. If you look at the ratio of GR to G0, G0 is the susceptance of the waveguide impedance, okay, which is in the 300 ohms and so, or 250 something usually. You can see that the offset is basically, you can control that ratio by the offset, which means you control basically, it's like a knob that you can tweak the excitation level of the slot. And that's good, because that's what makes the mechanism of basically tapering the coefficients. Now, let's look at quickly the radiation pattern from a slotted waveguide. We know that we have the elevation, and we have the azimuth, and we have side lobes in here, of course. And so you know that it goes like this. So we have the theta and phi, and the phi in this case, it's basically set to zero right now, okay, in this equation here. This is the array factor for these guys here. So you can see that the radiation pattern from a single slot multiplied by this twiddle factor in here will determine the radiation pattern of this, okay? And so in HFSS, what we do, we fix the phi and theta like this to monitor the azimuth and elevation pattern of the. So the meaning of what's meant by the theta and phi is explained in here. I just grabbed it so that some of you who may or not be antenna engineers, solid antenna engineers, they realize what these are. Now, like I said before, so we have the array pattern is like this as a function of theta, and we have these coefficients, and these coefficients basically is these derived from here, okay? And these coefficients are basically derived by realizing these based on a desired polynomial distribution, okay? And so that's why you end up you can control with these coefficients when doing the tapering these, you can actually control the side lobe level, okay? And here is an example that I put in here, which I will show in the coming session. I took this and laid out the equation, a half-wave dipole in here, and then some parameters in here, and some, these are the tapering coefficients here, and the GNs, and of course the XNs. So these are related, okay? And this is the hardest part of designing these. And of course, like in this case, this is 10 slots in this case. You can see that half of the slots are the same as the other half. So there is only 2, 4, 5 unique values. Otherwise, the other half is exactly the same, okay? All right, so let's start out with a design. I want to design a 10.3 gigahertz radar antenna aperture using the WR90 waveguide, standard waveguide. So so the first thing I would do is put the waveguide in HFSS and look at the pattern or the E-field pattern. Look at the half wave length between these, verify that the point from here to here is a half wave length at 10.3 gigahertz. Look at the higher order modes. Where do they happen at? Because what I want to do, for instance, I know that TE10, that first one, the cutoff is 6.7, 6.6 gigahertz. But then you can't use all the way up until, because you're going to hit the second a higher order propagating mode. You want to stay away from that. You want to stay below 40 dB on that. So basically, that's why this waveguide can only be used, say, until. So in my case, I want to use 10.3 at 10.3, which is marker 2 in here. You can see that this here is 80 dB down. So there's very unlikely that this mode will propagate. So let's look at the HFSS. So I've got so I came in here, and then I have this waveguide. So let's turn off the E field in here, so we can look at it. Let's leave the currents. So what I do is using the HFSS, I designed. You can see here the parameters. The A and B, you got 0.9 inches by 0.4 inches, and then I've got certain distances in here, like the thickness is 60 mil, 1.5 millimeter. And of course, you got lambda G and lambda 0. These are the numbers in here. And I'm using these so that I design the overall length of this. So the first thing I do is let's look at the current. You can see the current in here. Let me see if you can see it. Let me put on the E field so you can see it. So you can see that the current in here, you can see that the current distribution here. I want to put the slots so that, okay, let's look at, I'm feeding it from here, of course. Let's see the excitation. I'm feeding on this side here, the signal. Okay, so you can see that the current in here, how it's distributed, and we want to make sure, and you can see the sides as well, how the current is alternating in phase, And the same thing for the top, the broad wall as well. Okay, so you can see all of these, and of course you can check the S parameters, and you can see that the second order mode is actually happening at M3, which starts out at 13 gigahertz. Okay, so 10.3 gigahertz, I'm right here, which is good. So, okay. So that's as a first thing, because sometimes now, of course, for standard waveguides, these numbers are published, but you may end up with a custom waveguide, and that's where you would want to make sure that the operating frequency is appropriate, considering that the where it is relative to the higher. So as a very first design in a slotted waveguide, what I want to do is I want to construct a single slot. And that's basically what I have here. So what I have is I constructed a first slot, okay? And that first slot in here, okay, I'm feeding the signal on one side, the excitation here, and this is a slot. And I'm putting an air box on top to monitor the radiation from that slot, okay? And then, of course, the dimensions of the slot, I will go through that next week in the next session. But you end up with, of course, lambda G, lambda 0, which is the guide wavelength and the free space wavelength, and the slot width. I'm using this equation here, which is okay, published. That's what a lot of it. The slot length is basically the free space half wavelength. And then the slot offset from the center, as you can see, this one here. Now, if I go, let me put this back in the center, just to show you. Now, this one is 2.3. If I put 0 in here, now this is, as you can see, I put in the slot offsetted from the center, okay? And that's what basically makes it radiate. Otherwise, it does not radiate, okay? And for this one here, when I monitored, of course, now it's not really it's an antenna, but with two ports. In fact, you can see that I'm basically putting a wave port in here, and then I'm putting another port on the other side, and I'm monitoring. What I do is I monitor the transmission and the return loss, okay? And everything is fine. And then what I do is I look at the input impedance, okay? And this is exactly what this curve here that I showed you from this gentleman. This is this curve in here. This is showing basically how the impedance looking into this waveguide, the slot actually resonates at a half wavelength free space, and you get exactly that input impedance at that point to this waveguide becomes a pure resistance, and the imaginary part is 0. And that's what you see in here. You see this? Basically, if you put a marker at that point, I can't get it because well, let's see. Let's see if we can put it here. Oh, okay. Well, anyway, I put it right here. Well, this is the real part in here. This is the green one. At 10 gigahertz, you can see that it's resonating marker 3 at 10.32, okay, right now. So this is the resonance. This shows you that, yes, indeed, this waveguide here with this slot being 2.3 millimeters from the center of a W90 waveguide will resonate at 10.3 gigahertz. And then what I did is I set this up as an antenna. So I set my radiation sphere, basically the phi from 0 to 180, and then the theta from minus 180 to plus 180. And then what you end up with, you end up with a bunch of plots. Let's look at before I get to this one. You end up with exactly you can see the radiation pattern from that waveguide. So this is it. And you can actually look at the single cut where the gain in this is exactly 6 dB. And in fact, you can go also to the side lobe in here, and you can see that it's almost 16 dB down. Okay. And then you can let's see, you can view the gain at different frequencies. Like, and the reason I did this is because we do see multiple multiple resonances. You can see two lower resonances, but they're weak resonances from the magnitude of the resistance. Okay. What I'm interested in is this, but I said, let's go ahead and plot the gain at those two frequencies just to see it. And you can see that it's right here. It's pretty low. So the highest one is really at the frequency that I want, which is this one here, of course. And that is at 10.3 gigahertz. So this verifies, and of course, you can see the radiation pattern, the EM emission from the slot. You can monitor that and make sure it lands right on where it should be at. Okay, so let me just make sure that 10.3, okay, and this one is 10.3, just to make sure. Okay, because I'm solving at 3 different frequencies. So you can see that this is working, okay? So therefore now, so we did cover this. So the slot with these dimensions in here, you can see the current distribution as well, and the place of the slot, and verify that. The gain, we verified it. So you can really see that everything is fine with a single slot. But that's not really what we want. We want to build an aperture with a gain more than 30 dB, okay? And that's what we're going to do in the next sessions. So basically today, again, let's just roll back really quick what we did. We covered the principle of slotted waveguide, antenna array design, and 3D modeling. We want to shoot for designing an aperture like this, complete with a feed behind it like this, okay? But we started out with a single slotted waveguide with a single slot. Okay, we showed the differences of slotted waveguide antennas. We showed the principle of the current and where the slots are, why are the slots placed at a specific half wavelength from each other, and why is it from the side, a quarter wavelength from the shorter side. And then we showed the various different types of slots and why some do not radiate, because obviously they don't intercept the current flow. We showed the two different, the broad wall and the narrow walls, different polarizations for vertical and horizontal. We showed that the radiation pattern usually is basically orthogonal to the axis of the broad wall, so which makes it pretty neat. And then we showed that you can do all of this in substrate integrated waveguide if you like as well. We showed some examples of these antennas where they're used, and we showed the basically how you basically can size the aperture, and then from the size of the aperture come down to the number to figure out the number of slots that are required. Okay, of course, Mr. Elliott, with these publications, he's the father of this slotted antenna waveguide theory. He showed the design procedure for this, which is pretty simple. And I showed that we're going to use MATLAB to design these. Showed principally how the slots, theoretically, how they are impacting the radiation pattern as far as controlling the side lobe by controlling the distances from the center of the broad wall in here. Of course, the tapering of antenna feed networks, I covered that in a playlist, 4 parts. You can refer back to it. We showed the equivalent circuit impedance of the waveguide, input waveguide, as a function of the the slot length and the slot offset from the center line, okay? And that's basically, we showed that at resonance, you should be a half wavelength, the length of this is a half wavelength, and then the input impedance will be pure resistance, and the imaginary part will be 0. The radiation pattern, we showed that it's pretty simple. It's just the array factor is basically you take a single slot radiation pattern, which is a half wave dipole, and then you plug it into this equation here, which just basically shows it's a linear array in slots in here. Of course, we showed that we're going to use MATLAB to generate these coefficients, and we're going to come out and incorporate those into Elliott equations to figure out the distances, so we can implement these numbers in here. Okay, and then we started the design of 10.3 gigahertz slotted antenna waveguide, which we will use by looking at a single slot, what happens and how it acts as an antenna by itself. Okay, and we showed that. Okay, ladies and gentlemen, I'm Dr. Mohamed Nezami, wishing you good luck with your microwave and RF designs. Next week, we will iterate one more. There's going to be 4 parts to this, so it's or whatever number of slots. I get feedback usually on these videos, and that impacts what comes up. Usually, if there's researchers that are interested in some aspects of the design, usually I cover that. So please write me any notes that you would like. Okay, ladies and gentlemen, thank you very much and have a great day. This is Dr. Mohamed Nezami from Jerash, Jordan, wishing you the best.